Hello everyone, welcome back to my YouTube channel. In this video, I want to continue to solve the next 3 questions from EJU Physics 2018 second session, which is question number 7 until question number 9. You can check link on the description box below for the other solution on this paper, or check my EJU playlist if you want to watch the solution for another paper. Okay, let's start for question number 7. In this question, we have water of 5 times 10 to the power of 2 grams at 60 degrees Celsius is placed in a metal container at 20 degrees Celsius. So I have water and then I place it into the metal container. After sufficient time, the temperature of both water and the container becomes 50 Celsius. And then next, water of 1 times 10 to the power of 2 grams at 60 Celsius is placed in the same metal container at 20 Celsius. So we change the mass of the water, but we use the same metal container. After sufficient time, the temperature of both water and the container becomes T. The question is, if we assume the heat transferred is only between container and the water, what is the final temperature of our second case? So in this question, I have 2 cases. The first one is water of 5 times 10 to the power of 2, and I put it on the metal container at 20 Celsius. And then the next case is water 1 times 10 to the power of 2 grams with the same temperature and is placed in the same metal container. We want to find the final temperature of the second case. Since I do not know, or since the question do not tells us what is the specific heat capacity of water and the specific heat capacity of the metal container, so I think we can use the first case here to find the relationship between specific heat capacity of water and the specific heat capacity of the metal container. And then by using that information that we obtain from the first case, we can find the temperature of the second case. Okay, to relate or to solve question like this, you have to remember Black's principle. Black principles basically is the conservation of energy. As you can see here, water at higher temperature than the metal container, that means water will release heat, and then the heat that is released by the water is absorbed by the metal container. So I can write down Q is heat, yeah. Q released by water must be absorbed by metal container. This is the Black's principle. The principles is similar with the conservation of energy. To calculate heat or thermal energy, we can use formula mc delta T. M is mass, C is the specific heat capacity, and delta T is the change in temperature. So, mass of water 500, C of water we do not know, so I will write down as CW. Delta T of water initially 60, at the end 50. So the delta T of water is 60 minus 50, which is 10. Is equals to thermal energy of the metal. Remember that metal absorb heat. The initial temperature is 20, the final temperature is 50. So the metal container absorb heat that is released by the water. So if I want to calculate the heat transfer, if I want to calculate the thermal energy of the metal, I can use the same equation, which is mc delta T. I do not know the mass of the metal, so leave it as m. I do not know the specific heat capacity of the metal, I will write down as Cm. I know the delta T of the metal. The initial temperature 20, the final temperature is 50, then the delta T is 30. If you see from this equation, I can cancel out 0 here, 0 here and here, then m times Cm is equals to 500 over 3 Cw. Let me move my handwriting into here, yeah. 500 over 3 Cw is equals to mass of the metal container times the specific heat capacity of the metal container. Just leave it for now. We will use this relationship in our second case. For the second case, by using the same concept, as you can see here, the water has temperature 60 and then the metal container has temperature 20. That means the water will release heat, and the heat that is released by the water is absorbed by the metal. So the concept is exactly the same. But instead of 500, the mass of water now is only 100. So 100 times Cw times delta T, the change in temperature of the water we still do not know, because we do not know the final temperature of the container. The initial temperature of the water, the final temperature of both water and container is T, and of course T is less than 60. Because 60 is the temperature of the water will release heat. That means the temperature will drop. So T must less than 60. That means the change in temperature of water is 60 minus T. 60 minus T is equals to the heat that is absorbed by the metal, mcm delta T. The same thing, yeah? Except the delta T. Mass of the metal container times specific heat capacity of the metal container times delta T. Since the metal absorbs heat that is released by the water, that means the final temperature must greater than 20, the initial temperature of the metal container. That means to find delta T, we can use T minus 20, because now T is greater than 20. T minus 20. And then mcm here, I can substitute into 500 over 3 specific heat capacity of water. So substitute this box into mcm, then I will get 100 Cw 60 minus T is equals to 500 over 3 Cw T minus 20. As you can see, I can cancel out 100 here with 2 zeros there, and then I can cancel out Cw, and then I will cross multiply 3 to the other side. So I will get 3, 60 minus T is equals to 5 T minus 20. Of course, you can solve this equation. I will get 180 minus 3T equals 5T minus 100. And then at the end, I will get 280 is equals to 8T. That means T is equals to 280 divided by 8 is 35. This is the final temperature of the second case. So my final answer is number 3. This is for question number 7. Let's proceed to question number 8. For question number 8, I have a closed cylinder that is divided into two regions A and B by a smoothly moving piston. So as you can see in the diagram below, you have region A here and then region B there, and they are separated by a moving piston. The cylinder and piston are made of thermally insulating material. That means heat from outside cannot pass through the wall of the container. So heat from the outside cannot go into the region there, and also heat from inside cannot go out to the surrounding. And then there is a heater in A. In the region A, you have a heater. Ideal gases are enclosed in A and B in equal quantities. So you have ideal gas with equal quantities. Quantity of ideal gas is represented by the number of moles. The number of moles is usually write down as M. So if I write down here, the number of moles in region A is M. The number of moles in region B is also M. They both have the same number of moles. Initially, the gases in A and B have the same temperature, pressure, and volume. So initially, the temperature, let's say T, the volume is V, the pressure is P, and that for region B, the temperature is T, the volume is V, the pressure is P. So this is the initial condition for our ideal gases. And then the heater is now used to slowly heat the gas in A for a certain period of time. So we turn on the heater. Of course, the temperature of region A will increase. And then, as a result, the piston moves and comes to rest at a position where the volume of gas in A has increased by a vector of 6/5. They tells us that the volume of gas in A increased by a vector 6/5. That means if the initial temperature is V, as I write down here, the final volume is 6/5 V. I will write down here, the volume becomes 6/5 V, and of course the volume of region B will decrease. The volume is increased tells us that the piston has moved to the right. Since the piston is moved to the right, that means the volume of B is decreased. You can see that the total volume of this whole space is 2V. If the volume in region A is 6/5 V, that means volume in region B becomes 2V minus 6/5 V, which is 4/5 V. This is the final volume of region B. And then the temperature of A is TA, and then the temperature of B is TB. The temperature becomes TA, the temperature becomes TB. The question is, what is TA over TB? So I want to find the ratio of TA over TB. Before I answer this question, of course I need to know what happened to the pressure. Of course, the number of moles do not change because there is no ideal gases that is escaped from region A and region B. Since region A and region B are insulated, so number of moles do not change. But how about the pressure? As you can see from the information here, blah 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 blah, as the result the piston moves and comes to rest. This is the word that I will highlight. The piston comes to rest. Why the piston is come to rest? Because the force from A is equals to the force from B. As you know, pressure is equals to force over area. Since the force are equal and the area or the cross-sectional area of the piston is also the same, that means the pressure is the same. I do not know the value of pressure here. Maybe I will write it down as P prime. I believe P prime is different with P, but the one that I want to know is the pressure on both regions after we switch on the heater is the same. Okay? And then since we have an ideal gas, of course you can use equation PV equals to nRT. This is the basic equation for an ideal gas. I can rewrite this equation into PV over T equals to nR. N is the number of moles, R is the gas constant. For both region A and region B, N times R must be constant because the N are equal, and then the gas constant, yeah, of course, have the same number, yeah, or the same value for both region A and region B. So NR in region A must equals to NR in region B. That means PA VA over TA must equals to PB VB over TB. Just substitute all this quantity by using this, then I think we will obtain TA over TB. PA is P prime, and then VA is 6 over 5V over TA is equals to P prime VB 4 over 5V over TB. Of course, you can cancel out P prime and V, and then also the 5 here, and then by cross multiplying the expression you will get 6TB is equals to 4TA. That means TA over TB is equals to 6 over 4, which is 3 over 2. So our final answer for question number 8 is 3 over 2, which is number 6. This is my answer for question number 8. Let's proceed to question number 9, which is my last question in this video. For number 9, a fixed quantity of a monoatomic ideal gas, we have monoatomic ideal gas, is enclosed in a cylinder and its state is changed in the path A to B to C, as shown in the PV diagram below. So we have PV diagram. The question wants us to find the quantity of heat absorbed by the gas in the process A, B, C. We want to find the heat that is absorbed by the gas in the process of A to B to C. To solve question like this, you have to remember the first law of thermodynamics. I will use first law of thermodynamics First law of thermodynamics states that the change in internal energy of a system is equals to heat absorbed by the system, which is Q. This is the quantity that we want to find, plus work done on the system, which is W. This is the first law of thermodynamics. I will repeat it once again. First law of thermodynamics states that the change in internal energy of a system is equals to the sum of heat that is absorbed to the system and the work done on the system. When we use first law of thermodynamics, we have to remember the sign convention. Change in internal energy is positive if the temperature is increased. That means the change in internal energy is negative when the temperature is decreases. You have to remember this one. And then if heat is absorbed, that means Q is positive. So Q is positive when heat is absorbed by the system, and then negative when heat is released from the system. So absorbed is positive, and then release or emit is negative. And then last but not least, W is work done. W is positive is work is done on the system. And then W is negative is work is done by the system. When a work is done on the system, the volume mass increases. And then when the work is done by the system, when the work is done on the system, the volume mass decreases, and then when work is done by the system, the volume is increases. That is the sign convention that I usually use. Basically, if you have different sign convention, I think it's okay, but you have to be consistent. So you can use your own sign convention when we use first law of thermodynamics. But in this discussion or in this solutions, I will use my sign convention that I already explained before. Okay? And then one more thing that we should know when we want to solve the question is you have to know what is the formula of internal energy of an ideal gas. Internal energy of an ideal gas is 3/2 nRT. This is the formula of monoatomic ideal gases internal energy. And then, since we talk about ideal gas, as you know, PV equals to nRT. That means this nRT can be substituted by using PV. U equals to 3/2 PV. By using these two formula or these two concepts, I think we can find Q, which is heat that is absorbed by the process A to B to C. First of all, I need to find the heat that is absorbed from state A to B first. So we have to see the process A to B first and then B to C. For state A to state B, state A to B, first of all, I will calculate the change in internal energy first. delta U. Delta U is UB final condition minus initial condition. UB minus UA. UB is 3 over 2 PO to VO. PB VB ya, PB VB. So 3 over 2 PO to VO minus 3 over 2 PA VA. PO VO. If you calculate this, you will get 3 over 2 PO VO. This is the change in internal energy for state A to B. And then, if I want to calculate the work from state A to state B, you have to remember that work is the area below PV diagram. So when I want to calculate the work, I need to calculate the area. And then, since the volume is increasing, that means the work is done by the gas. You have to remember our or my sign convention. If you have forgotten, I think you have to watch this video again. I already explained it when I explained the first law of thermodynamics. Okay, so W, we can calculate W by calculate the area below the graph, and then since the volume increasing, that means the work is done by the gas. My sign convention for work is done by the gas is negative. So W is negative the area. The area of this rectangular is VO times PO. So the W is negative PO VO. After I got delta U and I got W, of course now I can calculate the Q for state A to state B by using first law of thermodynamics. So now I want to calculate the Q. My change in internal energy is 3 over 2 PO VO equals to Q, this is the quantity that I want to find, plus W, my W is negative PO VO. That means Q is equals to 3 over 2 plus 1, I got 5 over 2 PO VO. This is only for state A to state B. And then my last step is I will analyze state B to state C by using the same concept. So let us calculate state B to C. First of all, I will calculate the change in internal energy. Since I analyze B to C, that means the change in internal energy is UC minus UB. UC minus UB. UC is 3 over 2 PC VC. This is the formula, yeah. 3 over 2 PC, the pressure at C is 1 over 2 PO. VC, the volume at C is 3 VO. Minus 3 over 2 PB VB, PO times 2 VO. Okay, if we calculate it, I got 9 over 4 minus 3 which is 9 over 4 minus 12 over 4, negative 3 over 4. So delta U for the process B to C is negative 3 over 2. PO, VO. This is the change in internal energy. 9 over 4 minus 3, yeah? 9 over 4 minus 12 over 4, yep. Oh, negative 3 over 4. Sorry, my bad. Not 3 over 2, but 3 over 4. And then, for the work done, W, as you can see from the PV diagram, the volume from B to C is also increases. Since the volume is increases, that means work is done by the gas. If work is done by the gas, my sign convention is negative. So W is negative the area below the graph from B to C. So my W is negative area of this trapezium. Area of trapezium is sum of the parallel side, PO plus half PO, over 2. Times the height. The height is VO. If you simplify it, you will get 3 over 2 PO VO over 2. You got negative 3 over 4. PO VO. Okay, last step is by using the first law of thermodynamics, we can calculate the heat for process B to C. Delta U equals to Q plus W. We want to calculate the Q. I already know that delta U is negative 3 over 4 PO VO equals to Q plus my W is also 3 over 4, sorry, negative, I mean 3 over 4 PO VO. That means for this second process, my Q is equals to 0. That means there is no heat absorbed by the gas. So my final answer for the quantity of heat absorbed by the gas is heat that is absorbed in the first process plus heat that is absorbed by the second process. That means 5 over 2 POVO plus 0. So my final answer is Q total is 5 over 2 POVO plus 0, which is 5 over 2 POVO. That leads us to the final answer in number 5. Okay, that's it for this video. Thank you very much guys for watching this video till the end. I hope I see you guys on my next video. Thank you and bye bye.